Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today, we're undertaking a deep dive into the microscopic world of electric currents in conductors. This is from Unit 3, Current Electricity. Our mission is to solve one of the most fascinating paradoxes in physics and give you an exam-safe explanation that clarifies exactly how charge moves inside a wire.
Oh, this is great because I find this topic really confusing. The basic idea of electricity seems simple, but then suddenly we're talking about drift velocity and relaxation time, and it just gets very technical. It's hard to visualize.
Exactly, and that's our goal today. We are going to build a mental image so clear you'll never forget it. Let's start with a simple, everyday question. When you switch on a light, why does it turn on instantly? It seems the electricity travels incredibly fast, correct?
Yes, of course. It's immediate. If the current was slow, we would, see a delay, especially if the wire is very long. The effect is instantaneous, so the electricity must be moving at the speed of light, isn't it?
That's the logical assumption. And that perceived instantaneous effect, that's the core mystery.
Yeah.
Now, here's where it gets really interesting. If we could actually shrink down and track a single electron inside that copper wire, how fast do you think that one tiny individual electron is actually moving down the wire?
Well, based on what we just said, it must be moving extremely fast, maybe 3 into 10 to the power of 8 meters per second, something close to the speed of light, right? Otherwise, how can the effect be so quick?
And this is where we hit the physics paradox. Actually, in a typical copper wire carrying a standard household current, say 1 ampere, that individual electron is not zipping around at all. It is literally shuffling at a pace slower than a garden snail.
Slower than a snail? Wait, how is that even possible?
We're talking about speeds measured in fractions of a millimeter per second. The average net speed, what we call the drift velocity, or VDDR, is often around 0.07 millimeters per second.
0.07.
Yes. So this disconnect, an instantaneous electrical effect versus a snail-pace carrier movement, that is the great mystery we need to unpack. Understanding this is key. Okay, let's unpack this. The secret lies in the microscopic view of the conductor. The core idea is that inside any metal, the free electrons are always doing two things simultaneously. This is even before you connect a battery.
Okay, what's the first thing?
The first motion is their natural, rapid, and completely random movement. We call this thermal motion. Because the wire has some temperature, the electrons have thermal energy, and they zip around at phenomenal speeds, around 10 to the power of 6 meters per second. It's very fast, but totally random.
So if they're moving so fast, why don't they create a current on their own without a battery?
That's an excellent fundamental question. It's because the motion is random. For every electron moving left, there's another electron moving right. The net displacement is zero. It's like running very fast, but just in circles. You're moving, but you're not going anywhere.
Right, no overall progress.
Exactly. Now, the second thing happens when we connect a cell or a battery. When you do that, you establish an electric field across the wire. Think of this field like a very, very gentle slope. It provides a constant, gentle push. This push coaxes all those billions of randomly moving electrons to drift together in one coordinated direction.
So the current is not about the high thermal speed, the jiggling, but it's about that extremely slow collective push from the field. So the coordinated motion is what matters, not the random speed.
Precisely. This tiny coordinated movement is what we call the drift. And electric current is fundamentally the rate of flow of this coordinated charge. It's not the substance itself, but the rate at which this bulk coordinated charge flows through a cross-section of the wire. To make this really clear, think of our primary analogy. A massively crowded dance floor. All the dancers are jiggling very quickly in place because the music is loud. That's the fast, random thermal motion. Their individual energy is high, but they're basically stuck in the same spot. Net flow is zero.
Okay, I can picture that. So where does the battery come in?
The battery is like the DJ secretly tilting the entire floor just a tiny bit. That tilt is the electric field. Everyone still jiggles rapidly because of the music, but now they also slowly, collectively drift towards the lower end of the floor.
I see.
That slow creep downhill is the actual drift velocity, the $V, and the rate at which people pass the exit door. The collective count per second, that is the current.
Yeah.
Because there are billions and billions of dancers, that rate is huge, even if each person only drifts very slowly. The collective effect is powerful.
That makes so much sense. The dance floor analogy really helps.
Good. Now that we have the mental picture, let's get precise. We need to link this microscopic movement to the macroscopic current mathematically. Let's see how NSERT defines electric current. Could you please read the formal definition for us? for instantaneous current.
Yes. It says, reads verbatim, the current at time TSI across the cross-section of the conductor is defined as the value of the ratio of delta Q to delta 2 in the limit of delta T tending to 0. Okay, that definition is very precise, but it sounds complicated, especially the calculus part. Delta 2 tending to 0. Does this mean we always need calculus to define current?
That's a fair point. For our purposes, not usually. That instantaneous definition, delta 2 dollar, is really crucial only when the current is changing with time. For the steady currents we usually study in this chapter, the core idea is much simpler. Current dollar is just the total charge Q passing per unit time, so IQT. Now we need the technical bridge. We must show how that slow drift velocity, VDD analytically, relates to the huge current of dollars. It's a few logical steps. Step 1, the electric field E exerts a force, F equals QE, on every free electron. Since an electron's charge is negative, it tries to accelerate toward the positive end of the wire.
Okay, F equals EE. So the electron should just speed up continuously, like a rocket, right?
It would, in a vacuum. But not inside a conductor. That brings us to step 2. Before the electron accelerates too much, it immediately has a violent collision with one of the fixed positive lattice ions. These are the metal atoms. This collision is crucial because it basically resets the electron's forward momentum to 0.
Oh, so it's not a clear path at all. It's constant start, stop, start, stop.
Exactly. This cycle acceleration, then collision, then momentum reset, it repeats billions of times every second. Step 3. We define the average time between two of these collisions as the relaxation time. We use the Greek letter tau for it. So step 4. The electron only accelerates for this tiny time before the next collision hits the reset button. When we average this continuous cycle, we get the steady, incredibly slow drift velocity. VBD first Franz-Delt. It's tiny because tau itself is microscopic.
So the field gives a tiny push, but the collision immediately stops it. The net forward progress is only the tiny bit it moves during that time.
Perfectly put. And that net forward progress creates the current. Step 5 is the final link. The final and very essential microscopic formula is EDO OS G E A day IDO EC dot VB day. This formula is the key. It tells us that the measurable current dollar depends on the slow speed VDA, but also crucially on now, the sheer number of free electrons, E the charge of the electron, and AD out of the wire.
So a huge number of slow-moving things can still result in a large total flow.
That is the entire secret. Hope everything is clear so far. This concept explainer is from ProfSam.com, that is PROFSAM.com. Let's quickly use that simple example we mentioned earlier to really feel how slow VDollar is. Imagine a normal copper wire with a household current of just 1 ampere. Copper is extremely dense with 3 electrons. Its electron density, $, is massive. It's about 8.5 into 10 to the power of 28 electrons per cubic meter.
That's an astronomical number.
It is. Now, even if we use a standard wire with a cross-section A of 1 millimeter squared, we plug all these numbers into our formula, ADA, AV, maybe AVD, and we solve for VDollar.
And the result was?
The result is that VDollar is approximately 7.4 into 10 to the power of minus 5 meters per second. That's 0.07 millimeters per second.
So an electron would take hours just to travel a 1-meter wire.
Exactly. It might take over 4 hours to travel a standard 2-meter extension cord. It is genuinely staggering. So this brings us back to the main paradox. How does the light turn on instantly? This is the answer you must be able to give perfectly in an exam.
Is it because the electron at the switch doesn't have to travel all the way to the bulb?
Precisely. The key is to distinguish between the signal and the carrier. When you flip the switch, the electric field, that's the signal, propagates almost instantly through the whole circuit at nearly the speed of light. This means every free electron in the wire, from the switch all the way to the bulb's filament, responds and starts drifting simultaneously.
So the field is fast, but the charges are slow, like a long line of dominoes. The first one falls, and the effect travels instantly, even though each domino itself falls slowly.
That is a perfect analogy. The signal is fast, the carriers are slow. Now let's tackle the silent killers. These are common misconceptions that cost students marks. Killer number 1. Students often write that current is the speed of electrons. This is fundamentally wrong. Remember, current, $1, is a rate. It's Q-dollars that measures how much charge passes per second. It's a count. The actual speed is V-dollars, which is very slow. Never confuse rate with speed.
Got it. So I must always say the vice of the rate of flow of charge, because that rate depends on both the concentration dollar and the speed, VV Tyler, not just the speed.
Correct. Killer number 2. Why does the bulb light up instantly? We've covered this, but the wrong thinking is that electrons themselves must be fast. The correct answer is that the signal, the electric field, travels at nearly the speed of light, making all electrons start drifting at once.
The domino effect.
The domino effect.
Yeah.
Exactly. Killer number 3, and this one relates to our next topic, resistivity. Many students think resistance is some kind of friction, or that electrons are just lazy. Remember, resistance is caused by those violent collisions where electrons lose their momentum to the lattice ions. It's the interruptions.
So more collisions means a smaller relaxation time, which means less time to accelerate, and so higher resistance.
That is the perfect explanation. Resistance is all about collisions limiting the drift. More collisions means higher resistivity. We've covered a lot. So here are 2 quick memory anchors to lock this concept in. First, a simple phrase. Current is charge per second, not speed of charge. Just keep repeating that. Second, let's use a physical gesture. Wiggle your fingers rapidly in place. Go on, try it.
Okay.
That rapid wiggling, that's the fast random thermal motion. Now, while you're wiggling, very, very slowly move your whole hand downwards.
Ah, I see. The rapid jiggling is still happening, but that slow downward creep, that's the tiny drift velocity.
Exactly. That small overall creep is what creates the current. This dual motion is the essence of it all. All right, to wrap up, here are 3 exam-safe summary points you absolutely must remember. Point 1. Electric current IO dollars is the rate of charge flow. That is 1 $1 equals QLEHD. Its unit is the ampere. By convention, current flows from positive to negative, which is opposite to the actual electron flow. Point 2. This macroscopic current comes from the incredibly slow microscopic drift velocity of free electrons, which is superimposed on their rapid random thermal motion. The high-density neural electrons compensates for the slow speed. Point 3. Drift velocity is limited by constant electron lattice collisions. This mechanism, defined by the relaxation time tau, is the fundamental origin of resistivity in conductors. And a final thought for you. We know resistance comes from collisions. But if copper and glass are both made of atoms and electrons, why is copper 10 to the power of 23 times better at conducting? What is so special about its internal structure? That is a deep dive for another time. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is P-R-O-F, Sam, right?
Yes, ProfSam.com. Thank you for diving deep with us today.